Today we are going to discuss some problems related to size of the test and also power function of the test. Here the question is given a random sample of size n from normal with mean mu variance sigma naught square. Here sigma naught square means sigma value is unknown. Sigma value is known, right? For testing h naught, mu is less than or equal to mu naught versus h1, mu is greater than mu naught, and the test function is given by phi of summation xi equal to 1 if summation xi greater than k, 0 otherwise. Determine this k value such that size of the test equal to alpha. Also find out power function of the test. This is the question, right? Here random sample of size n from normal, mean mu and variance sigma naught square. Sigma naught square means the sigma square value is known. So if x follows normal with mean mu and variance sigma naught square, then what is the PDF f of x equal to 1 by square root of 2 pi into 1 by square root of sigma naught square into e power minus x minus mu divided by 2 sigma naught square, here x minus mu whole square, right? Where range of x is minus infinite to infinite and range of mu is minus infinite to infinite, where sigma is greater than 0, right? So here we have to determine the value k, right? So for that, first we have to find out the size of the test. What is the size of the test formula? Size of the test equal to supremum of expectation of phi of x under theta belongs to theta naught, right? For this in this problem, size equal to supremum expectation of phi of summation xi, theta belongs to theta naught, right? In this problem parameter is mu, right? So mu belongs to mu naught. So here in h naught, mu is less than or equal to mu naught, right? So then here mu is less than or equal to mu naught. So we have to find out for the which value of mu the expectation of phi of summation xi is attains supremum, right? For that we have to find it for the for which value of mu. We have to find out the value of mu for which expectation of phi of x attains supremum, right? For that first we have to find whether expectation of phi of summation xi is increasing function or decreasing function, right? So for that first we have to define beta of mu. So in this case parameter is mu, right? So we can take beta of mu. Beta of mu equal to expectation of phi of summation xi, which is equal to 1 into probability of, from test function we can write it as 1 into probability of summation xi greater than k plus 0 into otherwise, right? So beta of mu equal to expectation of phi of summation xi equal to 1 into probability of summation xi greater than k plus 0, right? Which is equal to probability of summation xi greater than k. So here we know that x follows normal mu sigma naught square, right? Then what is summation xi follows? We can take summation xi as y. Then y follows normal with mean n mu and variance n sigma naught square. Understood? So it is equal to probability of summation xi is equal to y, right? So y is greater than k, right? So which is equal to, we can write the term as integral over, and here we know that what is the range? Range is minus infinite to infinite, right? In this case, minus infinite less than y less than infinite. So here probability of y is less than, so y is greater than k, right? So we can write it as k, lower limit k to upper limit infinite, right? Then f of y dy. What is f of y then? So here f of x equal to 1 by square root of 2 pi 1 by square root of sigma naught square into e power minus x minus mu whole square divided by 2 sigma naught square, right? Then what is f of y? Here y follows normal with mean and mu and sigma naught square, right? Then f of y equal to 1 by square root of 2 pi into 1 by square root of n sigma naught square into e power minus 1 by 2 y minus n mu whole square divided by 2 divided by n sigma naught square. Here 2 is right. N sigma naught square into dy, right? So this is a long, it's a big term, right? So if it is difficult to derive, if difficult to integrate, right? So for that we can simplify this term to a small term. Okay, for that here we know that what is this term? Is a probability of y is greater than k, right? Where y follows normal and mu and sigma naught square, right? We can make these y term as standard normal variable. By minus n, the mean of that value, that is y minus n mu divided by square root of n sigma naught square, right? This is standard normal variable, right? Then variable minus its mean divided by its standard deviation, right? So it is less than k minus also this value minus mean divided by its standard normal variable, right? Then it becomes equal to probability of z, which is greater than k minus n mu divided by square root of n sigma naught square, right? Here y follows normal n mu n sigma naught square, then y minus its mean divided by standard deviation, which follows normal 0 comma 1, right? Here this is z follows normal 0 comma 1, right? Standard normal distribution, right? So which is equal to, it is the PDF of standard normal distribution. If z follows normal 0 comma 1, then f of z equal to 1 by square root of 2 pi e power minus z square divided by 2, right? Then here probability of z greater than k minus n mu divided by square root of n sigma naught square is equal to integral over, here lower limit is k minus n mu divided by square root of n sigma naught square to infinite, right? Then f of z dz, which is equal to integral over k minus n mu divided by square root of n sigma naught square to infinite. Then what is f of z? F of z is 1 by square root of 2 pi e power minus z square divided by 2 dz, right? So we have to, this is what is that, beta of mu, right? So we have to find out whether beta of mu is increasing function or decreasing function. For that we have to find out beta dash of mu, right? So here in limits is depending on parameters, right? Then f of z is not depending on the parameter, so we can use Leibniz rule, right? So using Leibniz rule, beta dash mu equal to, what is beta dash mu? So we can take these terms to differentiate, okay? Beta of mu, this term, okay? Beta of mu equal to f of infinite minus differentiation of infinite, it is 0, right? Minus then f of lower limit k minus n mu divided by square root of n sigma naught square into differentiation with respect to mu of the lower term, lower limit, k minus n mu divided by square root of n sigma naught square, right? Which is equal to minus, what is this value? That is here f of z equal to this value, right? Then what is f of k minus n mu divided by square root of n sigma naught square? That is 1 by square root of 2 pi e power minus k minus n mu divided by square root of n sigma naught square whole square divided by 2, right? Into d by d mu of k minus n mu divided by square root of n sigma naught square, which is equal to minus 1 by 2 pi square root of 1 by 2 pi e power minus k minus n mu divided by square root of n sigma naught square whole square divided by 2 into what is differentiation of these term? It is minus, here 0, right? Then here minus n divided by square root of n sigma naught square, right? Then which is equal to here minus minus, right? Minus into minus plus, right? So we can write it as here n divided by square root of 2 pi, then you can take the terms together. This square root of n sigma naught square into e power minus this term k minus n mu divided n mu square divided by square root of n sigma naught square divided by 2. Whether this term is greater than 0 or less than 0. This is greater than 0, right? That is beta dash of mu is greater than 0. It implies beta dash mu is greater than 0. Therefore beta of mu is non-decreasing function of mu, right? Then under h naught, what is h naught here? What is h naught here? H naught is mu is here in this case, h naught is mu is less than equal to mu naught, right? Mu is less than equal to mu naught. Then here under h naught, beta of mu is non-increasing function of mu, right? Therefore beta of mu attains supremum at mu equal to mu naught, right? Mu equal to mu naught. Then size of the test equal to, then size of the test, what is the size of the test? It is expectation of phi of summation xi under here mu equal to mu naught, right? Then here mu naught. For mu equal to mu naught, expectation of phi of summation xi attains maximum value, right? Which is equal to probability of summation xi, which is greater than k under mu naught. In this question is given that psi is equal to alpha, right? So which implies that here the size of the test is probability of summation xi greater than k under mu naught, right? And also it's given that psi is equal to mu. In this question it's given that psi is equal to mu. So which implies probability of summation xi greater than k under mu naught equal to the size of the test equal to probability of summation xi greater than k under mu naught, and also given that psi is equal to alpha, right? Which implies probability of summation xi greater than k under mu naught equal to alpha, right? Which implies, so we can simplify this term. We can transform this term as probability of summation xi. We know that summation xi follows normal with mean n mu and variance sigma naught n sigma naught square, right? In this case we can transform these summation xi as standard normal variable. For that, summation xi minus its mean, which means n mu, right? But here mu equal to mu naught, so we can take mu equal to mu naught divided by its standard deviation, that is n into sigma naught square, right? Then here also k minus n mu naught divided by square root of n sigma naught square, which is equal to alpha, right? Which implies probability of, this is standard normal variable, right? Which is z is greater than k minus n mu naught divided by square root of n sigma naught square equal to alpha. Which implies, so in this case we can use the table value. That means here this term we can write it as, here we want to find out the value of k, right? Here we want to find out the value for k. For that we can use the table values of standard normal normal distribution. So for that we can write this term as this term k minus n mu naught divided by square root of n sigma naught square, that is this term, then which is equal to, here probability of z is greater than this value equal to alpha, right? So we can write it as z alpha. That means this value is equal to the z alpha value given in the standard normal table. Understood? So here given that probability of z is greater than k minus n mu naught divided by square root of n sigma naught square equal to the alpha, right? So we have to find here in this problem we have to find out the value of k, right? So we can write these terms as k minus n mu sigma n mu naught divided by square root of n sigma naught square equal to this z alpha value. So this z alpha is determined from obtained from the critical obtained from the standard normal distribution table. Understood? So here z is greater than this value, it's equal to alpha, then you can write it as z alpha. Okay, here is probability of z is greater than alpha, so we can write z alpha. Understood? Then it's equal to, we have to find out here what is the k value, right? It's k equal to z alpha, then here n sigma naught square, then here plus n mu naught, right? That is k equal to n mu naught plus z alpha into square root of n sigma naught square. This is the value of k here. Then what is the rejection region in this problem? What is the rejection region? A rejection region. So in this problem is given that what is the test function? Test function is 1 if summation xi is greater than k, 0 otherwise. We know the interpretation of the test function, right? So from this test function we can say that we reject h naught, we reject h naught with probability, we reject h naught if summation xi is greater than k with probability 1, right? And also we reject h naught summation xi less than or equal to k with probability 0. Then what is the rejection region? Here this is the rejection region, right? We reject h naught if summation xi greater than k with probability 1. So here in this problem the rejection region is summation xi which is greater than k, right? So which implies that summation xi is greater than, we know the k value, that is this one, that is k is n mu naught plus z alpha square root of n sigma naught square, right? It implies here we want to find out the rejection region, rejection value. So that is z alpha value. We have to find out what is the z alpha value in standard normal table. Okay, so summation, which implies summation xi greater than n mu plus n plus z alpha into square root of n sigma square equal to, which implies summation xi minus n mu naught, sorry, n mu here, n mu naught, then divide by this term n sigma naught square, which is greater than z alpha, right? Which implies summation xi minus n mu naught divided by sigma naught divided by square root of n, which is greater than z alpha. This is the rejection region in this problem. And also in the question is given that how to find out power function of the test, right? Power function of the test. What is the power function of the test? That is here beta of mu, right? Here mu is the parameter, so we can take beta of mu here, which is equal to expectation of phi of summation xi, right? It's equal to probability of summation xi greater than k on the parametric space here, that is mu, right? It's equal to probability of summation xi. Here what is k value? K value is n mu naught plus z alpha square root of n sigma naught square, right, and the parametric space, right, which is equal to probability of, we can make this term as standard normal, this variable as standard normal variable, right. For that, summation xi minus here n mu or n mu naught, n mu, right, because here we take under parametric space, that means n into mu, right, divided by square root of n sigma naught square, right, is greater than n mu naught plus z alpha square root of n sigma naught square minus its mean, that is n mu divided by square root of n sigma naught square. Understood? This is the parameter. This is the power function of this test. Power function of the test means the probability of rejecting H naught under rejecting H naught for various values of parameter under parametric space, right? That means here probability of summation xi greater than this k value under parametric space. So we can take this as a standard normal variable. So here n, instead of n mu naught, here we take n mu because it's under parametric space. Understood? This is the power function of the test for this problem. Okay, next we are going to solve the another problem, and the question is given random sample of size n from normal mu sigma naught square distribution for testing h naught mu is greater than equal to mu naught versus h1 mu less than mu naught, and test function is given by, and here the test function is given by phi of x bar equal to 1 if x bar is less than k, 0 otherwise, and determine k such that size of the test equal to alpha, and obtain the power function of the test. This is the question. So here the question is given a random sample of size n from normal mu, mean mu, variance sigma naught square, which means the variance is known, right? For testing h naught mu is greater than equal to mu naught versus h1 mu is less than mu naught, and the test function is given by phi of x bar. Here x bar, okay, x bar means mean of x bar equal to 1 summation, sorry, x bar equal to 1 if x bar less than k, 0 otherwise. Phi of x bar equal to 1 if x bar is less than k, 0 otherwise. And the question is determine k such that the size of the test is equal to alpha. Obtain the power function of the test. Understood? And here what is size? Here size equal to supremum value of expectation of phi of x bar, right? Here test function is phi of x bar and the h naught. What's h naught here? Mu is greater than equal to mu naught. It is mu is greater than equal to mu naught. So in this case we have to find out what is the value of mu which attains expectation of phi of x bar is maximum, right? So for that first we have to write beta of mu, then find out beta dash of mu is increasing or decreasing function, right? Here what is beta of mu? Beta of mu equal to expectation of phi of x bar, so which is equal to 1 into probability of x bar less than k plus 0, right? So which is equal to probability of x bar less than k, right? Probability of x bar less than k. Here we know that x follows normal, mu and sigma naught square. Then what is x bar follows? X bar follows normal, mu and variance sigma naught square divided by n. Okay, then here we take let y equal to x bar, right, which implies probability of y is less than k. That is, we can write beta of mu equal to probability of y is less than k, which implies integral over lower limit is minus infinite, upper limit is k, right? Then f of u dy, right? Now what is f of u? F of y here minus infinity to k, f of y equal to 1 by square root of 2 pi 1 by square root of, here variance is sigma naught square divided by n, right? Then here standard deviation is, so here square root of sigma naught square divided by n, and e power minus y minus mu divided by sigma naught square divided by n whole power divided by 2, right, into dy, right? Here also this is a long term, right? Then it's difficult to integrate. For that we make some transformation, that is make these normal variable to standard normal variable. Okay, and here this term is equal to probability of y less than k, right? It's equal to probability of, we make this y as standard normal variable by y minus its mean equal to mu divided by its standard deviation, that is sigma naught square root of sigma naught square divided by n. This is less than k minus mu divided by square root of sigma naught square divided by n, right? Which is equal to, it's equal to what value? It's equal to probability of, this is z, right, standard normal variable. That is probability of z is less than k minus mu divided by square root of sigma naught square divided by n, right? Which equal to integral over lower limit is minus infinite, right? Minus infinite to this value, that is k minus mu divided by square root of sigma naught square divided by n f of z dz, right? What is f of z? F of z equal to, what is f of z? Equal to 1 by square root of 2 pi e power minus z square divided by 2, right? So which is equal to some integral over minus infinite to k minus mu divided by standard deviation, that is square root of sigma naught square divided by n f of z dz, right? So we have to differentiate beta of mu term, right? For that we can use also Leibniz rule, because the limits are depending on the parameters and f of z is not depending on the parameters, right? So here it's not depending on parameters, right? So using Leibniz rule, what is b dash of mu? B dash of mu equal to f of this value, right? F of k minus mu divided by square root of sigma naught square divided by n into d by d mu of k minus mu divided by square root of sigma naught square divided by n, which is equal to is equal to what value? Here f of k minus mu divided by square root of sigma naught square divided by n equal to 1 by square root of 2 pi e power minus, here f of z equal to 1 by 2 pi e power minus z square divided by 2, right? In the place of z we can substitute this value, right? That is e power minus k minus mu divided by square root of sigma naught square divided by n whole square divided by 2. Then differentiation of this part, that is into minus 1 by square root of sigma naught square divided by n, right? So whether this value is greater than 0 or less than 0, here minus down, right? So this is less than 0, which implies beta dash of mu is less than 0, right? So beta of mu is non-increasing function of mu, right? Here beta dash of mu is less than 0, so beta of mu is non-increasing function of mu, right? So we know that under h naught, what is it? H naught here under h naught. What's h naught here? H naught is mu is greater equal to mu naught, right? H naught is mu is greater than mu naught, right? Here also we know that beta of mu is non-increasing function. That means that is a decreasing function, right? Here lower limit is mu naught and infinite, right? So beta of mu attains maximum when mu equal to mu naught, right? So here under h naught beta of mu attains supremum at mu equal to mu naught, right? Understood. Then what is the size of the test? Then size of the test equal to expectation of mu naught phi of x bar, right? Here mu naught, right? When mu equal to mu naught, expectation of phi of x bar is attains maximum, attains supremum, right? Then we can take mu equal to mu naught, which implies probability of what is phi of x bar, that is x bar less than k, right? Phi of x bar is given, right, under mu naught. So here given that size equal to, in the problem is given that size equal to alpha, right? Which implies here also size of the test is probability of x bar less than k under mu naught, that is probability of x bar less than k under mu naught is equal to alpha, right? Which implies probability of, so we can make these normal variable as standard normal variable, that is z, which is less than k minus its mean means mu, right? But here under mu naught, so we can write it as mu naught divided by square root of sigma naught square divided by n, right? Which is equal to alpha. Understood this term. Here x bar is follows normal with mean mu and variance sigma naught square divided by n, right? So we can make this x bar term as standard normal variable, that is x bar minus mu naught divided by its standard deviation. It's equal to z. Z means standard normal variable. It's less than k minus mu naught, its mean, divided by square root of sigma naught square divided by n, right? So we have to find out the value of k, right? So for that we can make some transformation here. For that we have to make some changes, that is 1 minus probability of z is less than k minus mu naught divided by square root of sigma naught square divided by n, which is equal to 1 minus alpha. Here 1 minus probability of z less than k minus mu naught divided by square root of sigma naught square divided by n equal to 1 minus alpha. Here 1 minus alpha, and also here 1 minus alpha. Then what is the value of this term? 1 minus probability of z is less than k minus mu naught divided by square root of sigma naught square divided by n is same as probability of z greater than or equal to k minus mu naught divided by square root of sigma naught square divided by n, right? It's equal to 1 minus alpha. We can write only the critical value when z value is probability of z is greater than any term, right here. But in this case it's less than, right? So we make that less than to greater than term. For that we have to use 1 minus that value equal to 1 minus alpha. Understood? So which implies probability of z greater than equal to k minus mu naught divided by square root of sigma square divided by n equal to 1 minus alpha. So which is equal to, we have to find out the value for k, right? So we can take this term, it is k minus mu naught divided by square root of sigma naught square divided by n equal to, so then the z value, that is z 1 minus alpha, right? Understood? Here probability of z is greater than this term, right? Then this term equal to z 1 minus alpha value. We can obtain this 1 minus alpha value from the table, standard normal distribution table, which implies here we want to find out the k value, right? Then k equal to z 1 minus alpha square root of sigma naught square divided by n plus mu naught, right? Which implies k equal to mu naught plus z 1 minus alpha square root of sigma naught square divided by n. This is the value for k. Then what is the rejection region here? What is the rejection region here? In the test function is given that 1 if x bar less than k, 0 otherwise, right? That means we reject h naught if we reject h naught when x bar is less than k with probability 1, right? So this is the rejection region here. That means rejection region equal to x bar is less than k, right? Which implies x bar is less than, what is the k value? That is mu naught plus z1 minus alpha square root of sigma naught square divided by n, which implies x bar minus mu naught divided by square root of sigma naught square divided by n is less than z1 minus alpha. This is the rejection region for this problem. Understood? Then what is the power function of the test? Power function of the test, that is beta of mu. This is your homework. Okay.